In today's session, we're going to talk about the ideal gas law. The ideal gas law, or commonly known by its equation, PV equals to nRT over here. PV equals to nRT is a very well-known gas equation in chemistry. And in this chapter, we're going to use this formula quite a lot. And even in the next chapter, some of them will require this equation in your calculation, because when you want to know the pressure, the volume, the number of mole, or even the temperature involved for ideal gas, we're going to use this equation. Remember, we are talking about ideal gas. And then when we talk about ideal gas, you need to remember the assumptions of ideal gas. We have discussed about the assumption, the four basic assumptions for ideal gas, involving volume, intermolecular forces, motion and collision, and also the average kinetic energy. Okay, so when we talk about ideal gas, again, I repeat, you need to always try to relate that with this equation when you want to find the pressure, volume, number of mole, and even temperature. Okay, so how do we get this equation? So it's quite clear and it's quite obvious that by combining all the three gas laws that we have looked into in the previous exercises, by combining the Boyle's, Charles, Avogadro's law, you would be able to get your ideal gas equation. Okay, so I'm just gonna go through very quickly. We're gonna review very quickly what does it mean by Boyle's, Charles's, and Avogadro. So when you look at the relationship for Boyle's, volume is inversely proportional to pressure. So it means when the ideal gas volume expands, the pressure is going to be reduced. Okay? So when you look at Charles, when the volume of ideal gas is increased, the temperature of the ideal gas will also increase, because the relationship is directly proportional. Okay? And then when you look at Avogadro's law, the volume of ideal gas is also directly proportional to the number of mole of gas. So combining all three gas laws, you would be able to make this equation right over here, PV equals to nRT. So I think it's quite easy for us to remember the formula. I personally think that PV equals to nRT is one of the most, or the easiest formula to be remembered, because it rings quite well in your ears. Okay, so moving on to the next thing that we're going to talk about before we're going to look into a few examples. I just want to reiterate what does it mean by ideal gas. So it's very important that you need to assume that all of the gas that we're dealing with at your level, pre-university matriculation level, when we want to do a calculation about gases, we need to assume that all of the gases will behave ideally. Okay, so real gas is a different type of principle it will use. Okay, but for your syllabus, we're not going to be talking a lot about real gas. We're going to talk about that one later. But in terms of calculation, mathematics calculation, we're going to assume all of the gas behave ideally. Therefore, we can always use the formula PV equals to nRT to computate whatever things that you want to find. Pressure, volume, temperature, and number of mole of the gas. Okay, So remember, there's a word hypothetical over here. So it's a hypothetical gas. So the gas might be real in real life, but most of the time, we're going to assume that the gas exists. So it's hypothetical gas. So the gas might not be real. Okay, so we're just going to make the assumptions. And then remember, when does the gas behave ideally? When the space occupied by the gas we can ignore. Okay, so when we ignore the space occupied by the gas, the volume of the gas will be the same as the volume of the vessel the gas is in. Okay, so I hope that would be clear, because that is the most important principle that you need to understand when it comes to the volume of ideal gas. Because the ideal gas, the volume is too small, therefore we cannot really know what is the exact volume of the real gas. So we're going to assume that the volume of the gas is too small, therefore when we want to know what is the volume of the ideal gas, we're just going to assume that the volume of your ideal gas will follow the volume of the vessel. The word for vessel, sometimes they're going to use container, sometimes they're going to use balloon, sometimes they're going to use closed vessel, and so on. Okay, and then we need to assume that when does gas behave ideally? When there is no interactions. We need to ignore all type of intermolecular forces reacting between the gas molecules in ideal gas. Okay, so when they fulfill these two basic assumptions, therefore we can say that the gas will behave ideally. Okay, so remember the four basic assumptions or postulates. Some teachers, some researchers, some scholars, they're going to use the word postulates to replace assumptions. So by now you should be able to know that when we say assumption, it's the same as postulate. So in terms of ideal gas and in terms of kinetic molecular theory of gas, there are four basic assumptions that you need to know. So these are the four most important ones. Some people are going to have 5. They're going to talk about 6. But for matriculation, we're just going to focus on these 4. The most important one is going to be volume. We talked about it just now. So the volume of ideal gas is too small, therefore it's negligible, and therefore the volume of the ideal gas will be equivalent to the volume of the vessel. And then the intermolecular forces between the gas molecules, ideal gas molecules, can be ignored. And also we have talked about the motion, the molecules moving based on Brownian motion, and kinetic energy. So when you increase the temperature, the gas molecule is going to move even quicker. Okay, so those are the 4 basic assumptions, so it should be okay. Now, so when we're going to use the equation PV equals to nRT right over here, okay, we need to remember that this pressure, okay, the pressure must in it is must in ATM. Okay, pressure must be in ATM, so that is your pressure. And then your volume always going to be in liter or decimeter cubic, so it's the same as liter. And then mole over here, and your temperature must in Kelvin. So when you have something other than Kelvin, for example, you need to change it first to Kelvin. You need to show the conversion, okay? Let's say for volume over here, if we have something else like milliliter or other units, you need to change it first to liter. Why? Why do you need to do that? Because the value of R over here, okay, so R over there is this. So that is your R. R is a constant value. And this value will be given to you during exam. So you don't have to memorize this value. So why do we need to make sure your pressure needs to be in atmospheric pressure or ATM? Volume must be in liter. Temperature must be in Kelvin, because in the value of R here, the units is already in liter, ATM, mole, and Kelvin. So that is the reason why you need to convert all of the unit first according to the units of your R value. That is very essential. A lot of students, they have done this very simple mistakes, and because of that very small mistakes, they have lost quite a lot of marks. So please bear this in mind. Now, so just now we have talked about okay, so this is just, you need to remember, for volume of the ideal gas is going to be so small, therefore the volume of the gas can be ignored, okay, or negligible. Because of this assumption, we can always know that the volume of ideal gas will always going to be the same as the volume of your vessel. Okay, so this is a very, very important idea that you need to know. So sometimes the questions, they will not going to tell you the volume of your ideal gas. They're going to tell you that the gas will be filled into a vessel, or will be filled into a container, or will be filled into a flask with volume 1 liter per se. Therefore, when you know the volume of your vessel or flask or container, that will be the volume of your ideal gas as well. Okay, so don't panic if you get question. If it doesn't say what is the volume of your ideal gas, look for the volume of the vessel. Then remember this. So you should be okay. Now, when you look into your into the table of list of constants, you have two value of R. So which one do you need to use? Like I said, you need to use this one. Okay, so you just need to ignore that one. So you don't have to worry about this one. You just need to remember that one. 0.08 to 1 or 0.1. You can use either one. Okay, so remember that. This is just some conversion that you need to know. Now, let's try one examples over here. How are we going to use PV equals to nRT? So over here we have a very simple questions. It gives you a few information and it wants you to find things. Okay, so first of all, what I like to do over here, I need to know what does the question want. Okay, let's figure out what does the question want. So the question wants us to find out how many molecules, okay, how many molecules of nitrogen in here at that temperature, at that pressure. Okay, so that is what the question wants. The question wants you to find how many nitrogen molecules. Okay, so how do you find that one? If you still remember the Ma-Mo-Vono tree, to find the number of particles, okay, to find this, you need to find out what is the number of mole, okay? To find this, first, we need to find the mole of N2. Okay, we need to find the mole or N of N2 molecules. So how do we do that? We can use PV equals to nRT because we're dealing with gas over here. And like I said, in chemistry, we always going to be assuming that all of the gases will behave ideally. So when the gas behaves ideally, we can use the equation PV equals to nRT. Okay, so to find number of particles, we need to know what is the number of mole. So when we know the number of mole of nitrogen gas, we can multiply that with Avogadro's number, then we should be able to work it out. Okay, so what we need to do now, we're just going to list down what does the question gives. Okay, so the question gives, if we want to use PV equals to nRT, we need to make sure that we have pressure been given to you. So if you look here, we have pressure in millimeter mercury, so that is your pressure. And then we have a volume over here, and we have your temperature right there. So enough information is given to you, hence we can use PV equals to nRT. Okay, so pressure is about 1.00 times 10 to the power of negative 6 millimeter mercury. Remember, now, when you look at the units of your pressure, you know that you need to do some conversion because just now I've explained to you, if you want to use PV equals to nRT, you need to make sure all of the units going to be will be corresponding to the units of your R value. Okay, so P and then V here. V is given to you by 985 milliliter, and the one that we want to find is N. So this is what we want to find out. So when we can find this guy over here, we can use the Ma-Mo-Vono tree to work out how many N2 molecules are in the sample. Okay, so PV equals to N, so R is just 0.082 liter ATM per mole per Kelvin. And then the temperature given to us is about 0.0 degrees Celsius. So those are the informations given to you. Okay, so the first thing we need to do some conversion. Okay, remember, temperature needs to be in Kelvin. So if degrees Celsius is given to you, you need to add with 273.15 to convert Celsius into Kelvin. And then for pressure, you have this relationship over here. Then you just need to refer on that one. Is it given to you in exams? Yes. This relationship is given to you in exams, so you don't have to worry about memorizing the value. Okay? So the first conversion, let's convert the pressure. Okay? So when you look at the relationship here, 1 atm or 1 atmospheric pressure is equivalent to 760 millimeter mercury. Okay, for now, I'm just going to ignore all of this here because those are not used in the question. So the question uses millimeter mercury, mmHg. So from the equation, we know that 760 millimeter mercury is equivalent to 1 atmospheric pressure. And the question gives 1.00 times 10 negative 6 millimeter mercury, and we need to find out what is that value. So what do we need to do? If you want to find this, you're going to do cross multiplication. Okay, so when you go that direction, that is time. So you have 1 times 1.00 times 10 negative 6. And then when you go up, that one is divide. So you're going to divide by 760 millimeter mercury. And you will get about 1.315 times 10 to the power of negative 9 atmospheric pressure. So you have convert that one into that. Next, we're going to convert milliliter to liter. Okay, so the question gives you 985 milliliters. So to convert that is very simple. Divide by 1000, then you get 0.985 liter. Okay, so that's easy. Next, we're going to convert your temperature. So to convert your temperature, question gives you 0.0 degrees Celsius. So you need to add with 273.15. Then you get 273.15 Kelvin. So we have converted all of the values that we need to convert. So now we can move on to using this formula over here. Okay, so we have all of the values. Okay, so we need to find out what is this. What is the value of n over there? Okay, so to use that, we're gonna use PV equals to nRT. Okay, so when you rearrange all of that, you would get n equals to PV over RT. Okay, so it's a very simple formula. So when you solve that, you would get just now n equals to PV over RT. Yeah, so n just now, the pressure is about 1.315 times 10 negative 9, okay, times with 0.985, that is the volume, over 0.082, and then we have 273.15. So you should be getting somewhere around 5.781 times 10 negative to the power of negative 11 moles. So that is the this is the number of mole that we have found. So 5.781, we don't stop right over here, because what the question won just now, if we go back to the question, okay, the question wants you to find the number, okay, the question wants you to find how many molecules. So to get that one, we have worked out this. Now we need to times that with Avogadro constant. Okay, so we have to go all the way back to chapter 1. We have learned about this before. Okay, so when you look at this Mamo tree, you have this mole over here, and we want to find this, okay, number of particles, because we need to find out how many number of N2 molecules in that sample. And to do that, we need to follow this path. Okay? Again, you need to follow that path over here. So you need to take your number of mole, you need to multiply with your Avogadro's number. So the number of mole that we have gotten just now, okay, so the number of mole is about this number of mole is about 5.781 times 10 negative 11. Okay, and to get the number of remember this, the value is about 6.022 times 10 to the power of 23. So to work that out, very simple. So you're gonna get about, I'm just gonna do over here. So you're gonna get 5.781 times 10 negative 11 times 6.022 times 10 to the power of 23, and you should be getting something around 3.48 times 10 to the power of 13 N2 molecules. Okay? So that is the answer that you should be getting, 3.48 times 10 to the power of 13 N2 molecules. Let's try another example, shall we? So over here we have another example, and the question wants you to do two things. Number one, you need to determine the molar mass of your hydride. So it's quite different now. So just now we need to find out what is the number of particles. Okay, so for this question, you need to find out what is the molar mass. Just now, number of particles. And in this question, you need to find out what is the molar mass of your hydride. Okay, so we're going to do number A first. What we need to know here is, first we need to know what the question wants for this. So the question wants you to find molar mass. Okay? To get molar mass, you need to know that molar mass is mass over mole. So that is the formula of molar mass. Okay? Remember, the units for molar mass is gram per mole. So that's why you have mass over mole over here. Okay. So, as you can see, we have mole. Okay? Mole is N. And to find N, we can use PV equals to nRT. Okay? So when you want to use PV equals to nRT, you need to have pressure, volume, and T, because we need to find mole, right? So do we have pressure given to us? Yes, we have pressure right over here. Okay? So that is your P, pressure. Do we have volume? Okay, so let's have a look. Do we have volume given to you? We have contained in a flask of 385 milliliter. The question does not say what is the volume of hydride, but it gives you the flask, the volume of your flask. And remember, for ideal gas, we have talked about this just now. So the assumption is the volume of your ideal gas is negligible, can be ignored. Therefore, if you want to use PV equals to nRT, we can safely assume that the volume over here, okay, is gonna be the volume of your ideal gas as well. Okay, so we have your volume, you have your pressure. Okay, so now we have your volume right over here. And what about temperature? Okay, we have also temperature right over there. So that is your temperature. We have P, we have V, we have T, and obviously R is your constant, 0.02 1 or 0.0201. Okay, and you have mass. So given to you is this. Mass of your boron hydride, 6.3 milligram. So mass is already given to you. So mass is about 6.3 milligrams. Okay? But remember, for molar mass, your mass should be in grams. So 6.3 milligrams is also equals to 6.3 times 10 to the power of -3 grams. Okay? So the milli over there is equivalent to 10 to the power of -3. Okay, so we have done our, some very simple investigations on your question. We just want to find out what are the things that we need to use. So now we need to convert your pressure. We have identified that the pressure is about 11 torr. The question uses torr. The first one uses millimeter mercury, and this one right here, it uses torr, and we want to convert that into ATM. And from the relationship, we know that 760 torr is equivalent to 1 ATM. And the question gives you 11 torr. And we want to know how much is that in ATM. So again, we're going to do cross multiplication. So 1 times, so that is time. So you have 11 torr times 1 ATM So when you go up, that one is divide 760 torr. So you get somewhere around, you're gonna get somewhere around 0.0 0.0145 ATM. Okay. Next, we're gonna convert milliliter to liter. The question gives 385 milliliter. Remember, okay? Always remember that the volume of your container or vessel will equivalent to volume, okay, not value, volume of your ideal gas. In this case, we have the hydride. Okay, so remember this. This is a very important principle you need to know. Okay, therefore, that is the volume of your ideal gas, the hydride. So you have 385 milliliter divided by 1000, you get 0.385 liter. Okay, and then temperature, we have 25 degrees Celsius plus 273.15, and you should be getting 298.15 Kelvin. So that is the temperature. Now we're going to use this, okay? PV equals to nRT. We have this one sorted out, that one is sorted, and we get that one. Now we need to find out what is the number of mole. We know that the mass just now is about 6.3 milligram. Okay, is it 6.3? Yes, it is 6.3 milligrams. And now we want to find out what is the number of moles so that we can divide that with the value that we're about to work out. Okay. So again, when you rearrange this, you get N equals to PV equals to RT. We want to find N. So you get 0.0145 times with 0.385, that is the volume, over 0.082 times with 298.15. Okay, so just gonna remember that is your pressure, this is your volume, that is the value of R, and that is your temperature. And what you get, you're gonna get somewhere 2.283 times 10 to the power of negative 4 mole. Okay, so that is the number of mole that you have got. And to find the molar mass, remember, given is this in milligrams. So when you convert that, you get 6.3 times 10 negative 3 grams. Okay, so the molar mass of hydride should be 6.3 times 10 times 10 to the power of negative 3 grams over 2.283 times 10 to the power of negative 4 mole. So the answer is about 27.595 gram per mole. So you get that. So that is the molar mass of your hydride. Okay? So that is the final answer for this. Okay, so we have done that one. This is that one, final answers. And what about B? Okay, so for question B, which of the following hydrides is contained in the flasks? BH3, B2H6, okay, is it BH3? Is it B2H6? Or is it going to be B4H10? So which one of those three would be having this molar mass? So how do you do that? It's very simple. So first you need to identify what is the molar mass of your boron, and then identify the molar mass of your hydrogen. Okay, so we can do it one by one. So for the first one over here, boron is 10.8. So you're going to plus with 1.0 times 3 because you have 3H over there. Then you would be getting something like 13.8 gram per mole. Okay, so what about the one over here? You have 10.8, so that is the molar mass of boron, and then over here you have 2 times 2 plus 1.0, you have 6H times 6, then you get 27.6 gram per mole. And here you have 10.8 times 4 because you have 4 boron plus 1.0 times 10. So that is about 53.2 gram per mole. So which one of those three, which one of these three over here will be the closest to the one that we have worked out? So we have identified that the hydride, the boron hydride inside the flask, the molar mass is this, 27.595. So among all these three, which one is the closest? So that one is the closest. So the answer should be B2H6. Okay, so if you go back over here, if you go back to number B, the answer would be this, B2H6. So that is the molar mass of B2H6. Okay, so let's have a look at another one. Okay, the question wants you to find out find out what is the molar mass. We want to find out what is the molar mass of acetone. Okay, again, molar mass is mass in grams over mole. To find mole over here, we need to use PV equals to nRT. Okay, do we have pressure? Do we have pressure over here? Yes, you have pressure right over there, 745. Okay, so that is your P. Do we have volume given to you? Yes, you have volume of the flask, 247.3. Remember, for ideal gas, the volume of your ideal gas is equivalent to the volume of your flask, volume of your container, and volume of your vessel. So you need to remember that. And then what about temperature? Yes, temperature is also given to you. Okay, So it's very obvious that we have enough information. You have this, you have your temperature. Okay, you have your temperature over here, you have your pressure right over here, you have your volume right over there. So we can work out the number of mole first. Okay, so how do you work out that number of mole? We're going to use PV equals to nRT. Very simple. So the question gives you 7 for all of this. Okay, so these are given to you. Remember, for this one, this is equal to the volume of your acetone vapor. Okay, so in this case, your ideal gas. Okay, so that one is your ideal gas in this question. Okay, so that is the volume of your gas. So conversion, again, millimeter mercury to ATM, 760 millimeter mercury equals to 1 ATM. 745 millimeter mercury, so that is what the question gives. We need to find out what is that. You go here, times 1 ATM times 745 millimeter mercury. You go up, that is divide by 760 millimeter mercury. Then you get something 0.9803 ATM. Okay, then what about this? Question gives 247.3 milliliter. Divide by 1000, you get 0.2473 liter. What about your temperature? So you get 100 degrees Celsius, so that is what the question gives, plus 273.15 373.15 Kelvin. Okay, so we have converted all the things that we want to convert. Then you get something like this. Okay. So we want to find this. So you rearrange, you get that. Therefore, 0.9803, that is your pressure, times with the volume 0.2473, divide by 0.08237.3.15. So that is the temperature in Kelvin. Calculate that one using a calculator. You would be getting number of mole 7.9243. I like to take 4 decimal places when I want to calculate. To the power of -3 mole of acetone. We have worked out the number of mole. So, number of mole, we have got that one. Now, what about the mass? Okay, what about the mass of your, is given in the question. So when you go all the way back to the question just now, it's given to you, but you have to work it out. So when I'm just going to draw your attention over here, you have an empty flask with the mass of this. So when you fill that with acetone, the mass will increase. Okay, so mass of the acetone vapor, how do you get that one? You will take your empty flask, your filled flask minus empty flask. Your filled flask, you get, this one is 47.816 grams. You minus with 47.392 gram. So you get the mass of your acetone vapor is about 0.424 grams. So that is the mass of your acetone vapor. So it is quite tricky because the question does not say exactly in the beginning, but it gives you information. So the information given to you is the mass of the empty flask. Okay, so the empty flask, you get the mass over here, and then the mass of the flask when you filled it in with the acetone. So when you do some calculation, you would be able to get that value. Okay, so let's go back to there. So the mass, okay, so the mass of the acetone, you get 0.424 grams over mole 7.9243 times 10 to the power of negative 3 mole. So the molar mass is about 53.51 gram per mole. Okay, so that's how you work that out.